class, we have discussed how magnetic field is produced by electric current. We have learned that electricity can produce magnetism, that is, magnetic field is produced by electric current. Let us see what we have discussed in the last class. We have seen that substances are categorized into three based on how they interact with magnets. Those which are strongly attracted by magnets are called ferromagnetic substances. Those which are weakly attracted by magnets are paramagnetic substances, and those which are weakly repelled by magnets are diamagnetic substances. We have seen that a bar magnet is made from a ferromagnetic material, and we have seen how we can draw magnetic field lines around a bar magnet using a magnetic compass. We have also seen the pattern of magnetic field lines by using iron filings around a bar magnet. The magnetic field lines around a bar magnet are closed loops because north pole and south pole always occur in pairs. The direction of magnetic field lines outside the bar magnet are from north pole to south pole, whereas the direction of magnetic field lines inside the bar magnet are from south pole to north pole. We have seen how to represent the direction of magnetic field out of the paper. So, the direction of the magnetic field out of the paper must be represented by a dot, whereas the magnetic field which is directed towards the paper must be represented by a cross. We have discussed Oersted's experiment. Magnetic compass which will point towards north will get deflected when there is current in the wire. So, we have learned that current carrying wire has magnetic field around it. The direction of the magnetic field around a current carrying wire is given by right hand thumb rule, which says when a current carrying conductor is held by a right hand such that the thumb shows the direction of the current, the curled fingers will show the direction of magnetic field around the wire. The shape of the magnetic field lines around current carrying wire will be circular. We have discussed the experiment to see that the shape of the magnetic field lines around the current carrying wire are circular. When the current is out of the paper, the magnetic field lines are anti-clockwise, whereas current is into the paper, the magnetic field lines are clockwise. We have discussed the shape of the magnetic field lines around a circular coil. So, when a wire is bent into a circle and current is sent into the wire, the magnetic field lines around the wire are circular, and in the center of the circular coil the magnetic field is parallel as shown in the figure. Then we have discussed the magnetic field formed by a solenoid. When current flows in a solenoid, the magnetic field produced inside the solenoid is parallel, and the magnetic field is similar to that of a bar magnet. Children, in today's class we will discuss what is the force acting on a current carrying wire when it is placed in a external magnetic field, and why a current carrying wire has to get repelled or attracted when placed in a external magnetic field. Magnetic force acting on a straight current carrying wire. A magnet experiences a force due to external magnetic field. As a current carrying wire acts as a magnet, so the current carrying wire should experience a force in a magnetic field. Children, let us do an activity to observe the force acting on a current carrying wire in external magnetic field. For this activity we need a cell, a wire and a magnet. Here is the setup for the activity. Take a wire long enough to suspend through two pillars, and it is connected to a battery through a switch. Now, connect the wires to a battery by means of a switch. When we turn the switch on, we can see that the rod is pushed away. Now, let us change the direction of the current by reversing the battery. Now, we can see that the rod is pushed in the opposite direction. We can also do this by changing the direction of the magnetic field. Now, we use another pole of the magnet, we can see the direction of the force acting on the rod is reversed. Students, so we understood that a current carrying wire experiences a force when it is present in external magnetic field. So, we should find out what is the direction of the force acting on the current carrying wire. Why the current carrying wire experiences a force when placed in external magnetic field? The current carrying wire sets up its magnetic field around it. When placed in external magnetic field, both the magnetic fields will interact. So, when both the magnetic fields interact, we can see that because of the interaction between the magnetic fields, the wire will experience a force. As a result, the wire experiences a force. The direction of the force acting on the current carrying wire is known by right hand rule of positive charge. In this, we have to stretch thumb, index finger and middle finger mutually perpendicular to each other. The angle between these two is 90, these two is 90 and these two is 90. So, when all the three fingers are mutually perpendicular to each other in such a way that the index finger shows the direction of velocity of positive charge or current, the middle finger shows the direction of magnetic field, then the thumb shows the direction of the force acting on the wire. Children, consider a wire which is placed in external magnetic field. Here is the wire and there is no current flowing in it, and the direction of magnetic field is into the paper. So, when we pass the current in this wire, from the right hand rule we can find the direction of the force. Stretch your middle finger, thumb and index finger in such a way that the index finger will show the direction of flow of current, that is upwards, and the magnetic field is pointed by middle finger. Now, the thumb shows the direction of the force, that is towards left. So, whenever a current carrying wire is placed in external magnetic field, it will experience a force. Now, we have seen the direction of the force acting on the current carrying conductor when placed in external magnetic field. Now, let us see what is the magnitude of the force acting on the wire. The magnitude of force acting on the wire can be known by the formula F is equal to magnetic field times current times length, that is BIL. So, F is equal to BIL. In case if the direction of the wire is at an angle with the magnetic field, then the quantity is multiplied by the sin theta, where theta is the angle between magnetic field and the wire. Children, not only a wire, even if a charged particle which is moving in external magnetic field will also experience a force. This is because whenever a charged particle flows, it constitutes a current. So, this current will experience a force. Let us see what is the direction of the force acting on the charged particle. It will be similar to the force experienced by a wire. In the similar way, a moving charged particle experiences a force in external magnetic field. The direction of force can be known by the right hand rule. Now, consider a magnetic field which is into the paper. The velocity of the charged particle, which is q, is moving towards right. Now, using right hand thumb rule, we can find the direction of the force. The force is acting downwards and the magnitude of the force is given by BVQ, where V is the velocity, B is the magnetic field, Q is the charge. In case if the direction of velocity is at an angle theta with magnetic field, then the magnitude of the force is given by BVQ sin theta. Children, now let us see how a charged particle moves in external magnetic field. We have learnt in class 9 that whenever a force acts perpendicular to the velocity, as long as the force is perpendicular, the object only changes its direction and moves in a uniform circular motion. The same thing will happen with a charged particle, because as long as the charged particle is in magnetic field, when it is moving, the force acting on it will always be perpendicular to its velocity. Let us see how the force acts on the charged particle. Consider a magnetic field which is into the paper. Let a positive charged particle move in this direction. So, it will experience a force which is perpendicular to both magnetic field as well as velocity. This will be the direction of force. Because of this force, only the direction of the charged particle will change. So, its direction will change and it will move to this point. Because the magnetic field is still present there, the charged particle will experience a force which is again perpendicular to the velocity. As the charged particle continues to move, the force continues to be perpendicular. Hence, the charged particle will describe a circular motion like this. So, when a charged particle is moving in a magnetic field, it will describe a circular motion. So, we can conclude that magnetic force on a straight current carrying wire or a positive charged particle is in the same direction. Magnetic force on a straight current carrying wire or a positive charged particle is in the same direction. Let us see how this magnetic effect of electric current be used in electric motors. Children, if you observe in our day-to-day life, we use many electric motors. Most of the appliances are designed in such a way that they use electric motor and they reduce our workload. You name a device that will be more or less will be using an electric motor. Electric motors are used in day-to-day life in almost all areas. These are submersible pumps which are used to draw water from the wells or sumps. This is the coil inside an electric motor. In fan we use electric motors. In grinders we use electric motors. In crane we use electric motors. Refrigerators use electric motors to compress the air. Air conditioners use electric motors. Washing machine use electric motors. Now, let us see how electric motors work. Consider a coil which is placed in external magnetic field. In this arm AB, let the current is directed from A to B, and as the magnetic field is from left to right, we can find out the force acting on the wire, that is AB. By using right hand rule, we can see that the force acting on the arm AB will be into the paper. Similarly, the force acting on CD, because the direction of current is downwards, so here the force will be out of the paper. These two forces are acting in the opposite directions and away from the center. This will constitute a couple, that is, a turning effect is produced on the coil. So, when turning effect is produced on the coil will tend to turn. As it is mounted on a shaft which is represented by the green line here, the coil will start turning. The force acting on the arm AB will be into the plane, the force acting on the arm CD will be out of the plane. These two forces constitute a couple and produce a turning effect, and due to this turning effect the coil keeps turning. To continue the rotation of the coil, we need to change the direction of the current in the coil every half rotation. So, we use split rings as commutator to change the direction of current every half rotation. So, here is a DC electric motor, here the armature A, B, C, D, that is the coil, is mounted on a shaft, and here we use a commutator, that is split rings, which are connected to battery by means of a brush. So, brushes are just in contact with the commutator, but they are not permanently fixed. So, this allows them to be in contact with the commutator even though the motor is rotating. So, here when current flows from A to B, because of the magnetic field here, that is from north to south, the arm AB will experience a force downwards, while the arm CD will experience a force upwards. These two forces are parallel and opposite in direction, will constitute a rotatory motion. So, the motor will start rotating in anti-clockwise direction, and as the split rings are cut into half, at every half rotation the direction of the current will be changed. This makes the armature to continue to rotate for long time. Children, let us make a schematic motor to see how electric motor works. Here is a copper wire which is turned into a loop. The arrangement is so made that the loop is free to rotate. Now, we use a circular magnet, we can also use a bar magnet to provide external magnetic field, and a cell is used to provide electrical energy. Once we provide electrical energy by connecting to the cell and give a gentle push to the loop starts turning. Here we can see how the loop turns. We need to give a gentle push to the loop because here the magnet is only in one direction, that is north pole is at one side, and the direction of magnetic field is not strong enough. Because the loop is very light and there is no load, it continues to turn even if we do not change the direction of the current. Whereas, for practical motors which we use to do work, they will have load, hence a commutator is a must. This is a DC electric motor because we use a DC power supply, that is direct current. The direction of the current will not be changed by the power supply. Children, so we have seen a schematic motor which runs by means of a small battery and in the presence of external magnetic field. When this motor cannot be used to rotate or take load, because this is a small motor, it only can run taking this light weight. If we use a commutator and more number of coils, then the motor can generate enough torque to take the load. Children, the speed of the motor will depend on the strength of the magnetic field, the area of the coil, the current in the coil and the number of turns in the coil. So, you may see different motors are used for different purposes, and to take different loads the size of the motors will change. You need a small motors in toy cars to take a small load, whereas for mixer grinders the size of the motor is little bigger. If it is a wet grinder which can grind a heavy load, can need to be a bigger in size. And you may also see the motors which are even bigger, big as the stable, for generating very high speed, like in aeroplanes, where to produce the wind speed they need to have a very big motors which can generate 25,000 RPM. So, motors are designed for different purposes. The size, the armature of the coil which is used, the area and the number of turns will matter the torque and the speed of the motor. Children, now let us revise. We have seen that magnetic force on a straight current carrying wire or a positive charged particle is in same direction. The direction of the force can be known by the right hand rule, that is, when three fingers, thumb, index finger and middle finger are stretched in such a way that they are mutually perpendicular to each other, and the pointer shows the velocity of the charged particle or current and middle finger shows the magnetic field, then the thumb will show the direction of the force acting on the wire. The magnitude of the force acting on the charged particle is given by BVQ sin theta. This is how a charged particle will move in a circle, making uniform circular motion in external magnetic field. The right hand rule of positive charge can also be applied to find the direction of force acting on the current carrying wire in external magnetic field. So, the direction of force acting on the wire in external magnetic field is given by right hand rule, and the magnitude of the force acting on it is given by BIL. A current carrying wire experiences a force in external magnetic field as the magnetic field produced by the wire and the external magnetic field interact. We have discussed DC electric motors, which will rotate by means of a commutator. As the direction of the current is changed for every half rotation, the armature keeps turning. It continues to rotate as the direction of the current changes every half rotation. We have seen how the torque is generated on a loop of electric motor. The speed of the rotation depends on the strength of the magnetic field, area of the coil, current in the coil, and number of turns in the coil. Children, I suggest you to observe different electric motors used in our day-to-day life and appreciate how electric motors have made our life easy. In the next class, we will discuss how electricity is generated by electromagnetic induction. Until then, thank you.